Hi, welcome to another video by tekcerpts. In this tekcerpt, we are going to discuss another applications of neural networks. Object tracking is the process of following an object's movement in a video over a time. This task is challenging because of changes in appearance, lighting, and occlusions. To tackle this problem, convolutional neural networks remain the most used and reliable network for object tracking. However, multiple architectures and algorithms are being explored as well. Among these algorithms are recurrent neural networks, autoencoders, generative adversarial networks, CMEs neural networks, and custom neural networks. So, usual flow of multiple object tracking algorithm includes mainly 4 steps. As for the first stage, it's a detection stage. An object detection algorithm analyzes each input frame to identify objects belonging to the target classes using bounding boxes, also known as detections, in the context of multi-object tracking. Feature extraction prediction stage is the second step, where one or more feature extraction algorithms analyze the detections and use tracklets to extract appearance, motion, and interaction features. Optionally, a motion predictor predicts the next position of each track target. Affinity stage is the third one. Here, features and motion predictions are used to compute a similarity or distance score between pairs of detection and tracklets. As for the final stage, which is association stage, the similarity or distance measures are used to associate detections and tracklets belonging to the same target by assigning the same ID to detections that identify the same target. So, if you want to implement object trackings by yourself, then let's go through some of the examples. You can use the opencv library, which is open source. There are multiple trackers that you can use. For example, use CSRT when you need higher object tracking accuracy and can tolerate lower FPS throughput. Use KCF when you need fast FPS throughput but can handle slightly lower object tracking accuracy. Use Mose when you need pure speed. Or you can use deepsort, which is one of the most widely used object tracking frameworks. Appearance information is integrated within the algorithm, which vastly improves deepsort performance. Because of the integration, objects are trackable through longer periods of occlusions. This will reduce the number of identity switches. Additionally, the computer vision toolbox in MATLAB provides video tracking algorithms. Another option is to use MDNet. It's a fast and accurate CNN-based visual tracking algorithm inspired by the RCNN object tracking network. It functions by sampling candidate regions and passing them through a CNN. The CNN is typically pre-trained on a vast dataset and refined at the first frame in an input video. Okay, so now you have some idea of object tracking. Let's go to the pose estimation, specifically human pose estimation. It's a way of identifying and classifying the joints in the human body. There are classical and deep learning methods for the human pose detection, but in this tekcerpt, we are mainly going to focus on the deep learning approach. One of the recent challenges in pose estimation is to tackle multi-person pose detection. Deep neural networks are very proficient in estimating single human pose, but when it comes to estimating multi-human pose, they struggle due to an increase in computational complexity and high inference time. In order to tackle these problems, the researchers introduced 2 approaches. The first approach is the top-down approach, which is to localize the humans in the image or a video and then estimate the parts followed by calculating the pose. And the second one is bottoms-up approach. Here, it estimates the human body parts in the image followed by calculating the pose. So, one bottom-up approach is opencv, which uses CNN as its main architecture. It consists of a VGG19 convolutional neural network that is used to extract patterns and representations from the given input. The output from the VGG19 goes into 2 branches of convolutional neural networks. The first network predicts a set of the confidence map for each body part, while the second branch predicts a part affinity fields, which is called as PAFs. This will create a degree of association between parts. It is also useful to prune the weak links in the bipartite graphs. Let's look at a pose estimation algorithm that uses a top-down approach. For example, you can use regional multi-person pose estimation, which is called as RMPE in generally, or alphapose. The main problem tackled by the alphapose is to extract a high-quality single-person region from an inaccurate bounding box. This imperfect human detection, like in this image, overcome using two-step framework identified by the authors of alphapose. The first part of this two-step framework is Symmetric Spatial Transformer Network, also called as SSTN. This will help to crop out the appropriate region in the input, which subsequently simplifies the classification task, leading to better performance. And the second pass is Single Person Pose Estimation (SPPE), which is used to extract and estimate human pose. This two-step approach increases classification performance by tackling invariance while providing a stable framework to estimate human pose. Alright, let's start with the basics of reidentification, or reid for short. This is the process of identifying the same person across different locations or time instances, typically through surveillance footage or images. It's like matching a person's identity from one camera to another. One of the popular examples of reidentification is alignedreid++. This is an advanced framework built on the foundation of deep learning. It's designed to enhance the accuracy and efficiency of persons' reidentification. This will work by aligning images and learning discriminative features. It's like giving AI a supercharged pair of glasses. One of the standard features of alignedreid++ is its focus on carefully aligning images before it processes. This alignment mitigates the challenges posed by variations in pose, lighting, and camera angles, leading to more reliable results. Part-based convolution baseline is a critical component of alignedreid++. It divides the person's image into horizontal stripes, each containing specific body parts. This separation allows the model to focus on individual parts, making it more robust to appearance variations. Here's how alignedreid++ work in a nutshell. First, the input image is aligned, breaking it down into parts. Next, the model extracts the powerful embedding from these parts. Finally, it uses these embeddings to match and identify individuals across different instances. Alignedreid++ isn't just about accuracy, it's also about efficiency. By focusing on body parts and leveraging aligned features, it is significantly improves both the precision and the speed of person reidentification. So to summarize what we discussed in this tekcerpt, first we looked at object tracking using neural networks, and we went to discuss human pose estimation and reidentification. For all these applications, we provide example neural networks currently under use and a way of using them. So, if you enjoyed this tekcerpt, please like and share. If you have any suggestions, feedbacks or questions, don't hesitate to comment. And to stay tuned, please subscribe and hit the bell icon. See you soon.